Right, so good afternoon again, everybody, and we are now taking a look at the conditions for equilibrium. So, in the previous video, we came across the principle of moments, and we said that the principle of moments states that for a system in equilibrium, the sum of the anti-clockwise moments is equal to the sum of the clockwise moments, or vice versa, about some fixed turning point. Alright, so for something to balance, we knew that, of course, the clockwise turning effect must be equal to the anti-clockwise turning effect. So that, of course, must be satisfied for a system to be in equilibrium. So there is also another condition for equilibrium, and we're going to take a look at that today. But also, we want to see how the principle of moments can be translated into an actual mathematical formula so that we can actually make some sort of calculation with it, determinations with it. So I'm just looking at a very simple system here where we have this uniform plank, looks pretty much like a seesaw, all right, and it's pivoted at this point, and we have two masses, mass A and mass B. Mass A has a mass of 100 kilograms and therefore a weight of 1000 newtons. Weight is mass by gravity. So in this case, 100 by 10 gives us 1000. Similarly, B has a mass of 200 kilograms and therefore a weight of 2000 newtons. B is 1 meter away from the pivot, whereas A is 2 meters away from the pivot. Now, if you look at the diagram carefully, I also introduced another force. And that other force is the upward force given by this pivot here. Because the pivot is, of course, supporting the plank and both the masses. Now, this is a uniform plank. And what we must remember about it, something that is uniform in dimensions, is that the center of gravity will be at the center, very much like me here supporting this meter rule at the 50 cm mark, and therefore it is in equilibrium. So you get an upward force here as well. So let's take a look at the principle of moments one more time, and let's just see how it translates now into an actual equation. So let's read. The principle of moments, the sum of the anti-clockwise moments equals, and that's the very, very critical thing, equals the sum of the clockwise moments about that same turning point. So we can now translate this actual sentence, this actual principle, into an actual formula. Sum of clockwise moments equals sum of anti-clockwise moments. We now have an equation, and with an equation we can, of course, determine different quantities. So let's look at it. 2000 newtons, which was, of course, the clockwise moment provided by B, because if you think about it, if you pull down this way, this system will want to rotate in this clockwise manner. And if you pull down this way, this system is going to want to rotate in an anti-clockwise manner. So 2000 newtons multiplied by 1 meter and 1000 newtons multiplied by 2 meters, as you can see here. And since they have both equal amounts of turning effect, right, clockwise movements and anti-clockwise movements, this system happens to be in equilibrium. The other condition for equilibrium to take place, right, and I'll state it right here, is that the sum of the forces in one direction must be equal to the sum of the forces in the opposite direction. So let's go back to the diagram. This wooden trestle, as it's very often called, this trestle, right, this support, is actually supporting, again, the plank and these two masses. So the plank has a weight, and the weight of the plank will act through its center of gravity. Remember, the center of gravity is the point through which all the weight of the object seems to act. And since this plank is uniform, all the weight will act downwards, but in this case it's being supported by the trestle, this pivot here, and getting an upward force. So the sum of the forces in one direction, there are two directions here. There's forces acting upwards and there are forces acting downwards. The two forces acting downwards are, of course, the weight of A and the weight of B. So A plus B gives us 3,000 newtons. So that means that the upward force provided by this trestle to support this system is 3,000 newtons, right? Sum of forces in one direction going up is equal to the sum of the forces in the other direction, in this case going down, right? So it's not always, in some books or in some teachers may also say upward forces equal downward forces, but very often I like to use forces in one direction equal forces in the other direction, because very often it's not always upwards and downwards forces we are looking at. We may be looking at forces acting to the right and to the left, or to the east or to the west, and as a result we have to make sure that we say it in a manner that encompasses all equilibrium, and that would be sum of forces in one direction equals sum of forces in the opposite direction. So we are going to use these two conditions now, right, to be able to solve some of the CSEC questions. So in the next video we're going to take a look at one of the CSEC questions from a past examination. These questions are open source. They are free to be downloaded from the CSEC website, and I'm stating that only because I want to be clear of any copyright infringement issues. Okay, so I'll see you in the next video.